Okay, so this video is meant to be a self-contained proof of the Jacobi triple product identity. So we'll set up all the relevant notation, we'll set up all the relevant lemmas, and we'll finally prove the Jacobi triple product identity and just various reformulations of the Jacobi triple product identity. So we can see the identity list written here. It's a rather elegant identity. It's a nice infinite sum equal to a nice infinite product. This identity is rather fundamental. It's used quite a bit when doing number theory, especially in study of Q series. So our goal is going to be to prove this, and we'll need this to rewrite our Rogers-Ramanujan identities later on. Okay, so let's begin. So the first thing I'll note is that all symbols that I use, so for example, I'm going to use A, T, Q, X, etc., are formal variables. Okay, so all these guys are just going to be formal variables. And just to recall that we're going to interpret 1 over 1 minus q, or 1 over 1 minus any variable or combination of variables, as a geometric series. So this is just meant to be the sum of q to the n as n goes from 0 to infinity. And if we write this out, this is just 1 plus q squared, so on and so forth, right? Your standard geometric series. Okay, so we begin by introducing what's called the q-Pockhammer symbol. So this is the q-Pockhammer symbol. And what we're going to write is a semicolon q sub n. This will be taken to mean the product 1 minus a, 1 minus aq, 1 minus aq squared, and we keep going until we reach 1 minus a q to the n minus 1. And more compactly, we can just express this as the product 1 minus a q to the k, as k goes from 0 to n minus 1. All right, and we'll define this for n bigger than or equal to 1. So this will be a fairly standard notation. It's used a lot in number theory. We'll be using this to represent this infinite product. We will define a semicolon q sub 0. All right, this will just be defined to be 1. And then finally, we'll define the infinite product aq infinity. This will just be the product 1 minus a q to the k, as k goes from 0 to infinity. So it's the same product as aq sub n, except we let n go to infinity, right? So we have an infinite product rather than a finite product. So this is our q-Pockhammer symbol. And there's a very standard kind of shorthand for this q-Pockhammer symbol. So we write, when it's clear that q is the variable we're incrementing by, we'll write a sub n for a semicolon q sub n. And we'll often write a sub infinity. Fix that typo, a sub infinity, for a semicolon q sub infinity. Okay, so one might ask the question, well, what properties does this have? How can I do mathematics with this? So some of the fundamental properties we'll write down now. The first property is that a sub n can be written as a sub infinity divided by a q to the n sub infinity. The second fundamental property that we'll need is that negative a sub infinity times a sub infinity is actually equal to a squared semicolon q squared sub infinity. And the third property will be that 0 sub infinity is equal to 1. So these are our first three fundamental properties, which we'll prove about this q-Pockhammer symbol. So let's begin the proof of these. The proof is rather straightforward. So let's prove property 1. For property 1, I'll start with the right-hand side. I'll write a sub infinity divided by a q to the n sub infinity. And let's expand these products out. So the product in the numerator is just 1 minus a, 1 minus aq, 1 minus aq squared. And it just goes on infinitely. So we'll keep going. We'll write 1 minus a q to the n minus 1, 1 minus a q to the n, 1 minus a q to the n plus 1, so on and so forth. The product in the denominator, so what we're doing is we're taking our q-Pockhammer symbol and replacing all the instances of a with a times q to the n. So our beginning term is 1 minus a q to the n. And we're incrementing by powers of q. So the next term is going to be 1 minus a q to the n plus 1, 1 minus a q to the n plus 2. And this is an infinite product, so this goes on forever. And one thing that we notice is that there's some nice cancellation that happens. Namely, this 1 minus a q to the n cancels with the numerator. This 1 minus a q to the n plus 1 cancels with the term in the numerator, and so on and so forth. We see that there's an infinite amount of cancellation, which happens. And what do we end up with? This is just 1 minus aq, so on and so forth. And we stop at 1 minus a q to the n minus 1. But what is this symbol? This is none other than a sub n, right? So this is a proof of the first one of these properties. And we'll be using this quite regularly. Okay. For the second property, we'll start with the left-hand side and write it out and just see what happens. All right, so for the second property, I'm going to start with minus a sub infinity, and let's write out this product. So the first symbol is saying replace a with negative a. So the 1 minus a q to the power term become 1 plus a q to the power term, because subtracting a negative a turns it into a sum. So this is going to be 1 plus a q to the k, as k goes from 0 to infinity, times the product of 1 minus a q to the k, as k goes from 0 to infinity. We combine these products. We notice that this is going to just be the product k goes from 0 to infinity of 1 plus a q to the k, 1 minus a q to the k. And when we multiply these out, what do we see? Well, we get 1 minus a squared q to the 2k, as k goes from 0 to infinity. So we multiply these two terms out. And then the thing that we notice is that this is none other than a squared semicolon q squared sub infinity. So this is the Q-Pockheimer symbol, where you've replaced a with a squared and q with q squared. Okay, so that's property 2. And property 3 is actually probably the easiest of the three. So let's prove property 3. So namely that 0 sub infinity is equal to 1. So let's write this out. So property 3, I have 0 sub infinity. Well, what does that mean? That means I'm taking my Q-Pockheimer symbol and replacing a with 0. So I'm getting the product of 1 minus 0 q to the k, as k goes from 0 to infinity. And what does that leave me with? Well, that's just an infinite product of 1s. 1 times 1 times 1 times 1, so on and so forth. And so this product is equal to 1. All right, so we've established our 3 properties. So our next result will be the following theorem due to Cauchy. So I've written it here in Q-Pockheimer notation. If we choose to expand everything out and not use the Q-Pockheimer notation, the theorem can equivalently be written this way. So all I've done is I've expanded out the a sub n, the q sub n, the at sub infinity, and the t sub infinity out for you. So this result will be quite fundamental because its corollaries will be important to us when we prove the Jacobi triple product identity. But the proof of this result is also actually quite interesting. So the proof involves basically finding a recursion that these identities satisfy and then using that recursion to compute the sum side. So let's begin with this proof. So let's start the proof of this theorem. So the first thing I'm going to do is I'm going to say let f of t be our product side. So f of t is going to be the product as n goes from 0 to infinity of 1 minus a t q to the n divided by 1 minus tq to the n. And we'll write out the sum side, right? So the one thing to notice is that this is a power series in a, t, and q. So the denominators, so the denominator can be expanded as 1 plus stuff. And the numerator is all 1 minus stuff. So there are no negative powers of q or negative powers of any variables that occur. But what we'll do is we'll actually write this as the sum of a sub n t to the n as n goes from 0 to infinity. All right, so we notice that in particular, this is a power series in t. And the a sub n's, of course, depend on a and they depend on q. So these aren't constants. They depend on our variables a and q. Okay, so the first thing that we're going to notice is first, we note that if I substitute t equals 0, my numerator becomes 1 minus 0 over 1, or rather my product becomes 1 minus 0 over 1 minus 0. So I just have an infinite product of 1s. So this is equal to 1. And if I substitute t equals 0 in my sum expression, I just get a sub 0 because the other terms are a1 times 0 plus a2 times 0 squared plus a3 times 0 cubed, so on and so forth, right? So one thing I notice right away is that a0 is equal to 1. Okay, so where do I go from here? Well, the other thing I might notice is that there's a recursion that this will satisfy. So what do we do next? Next, I'll take 1 minus t times f of t. And let's see what we get when we look at this expression. All right, so I'm going to, again, use the product side for this. So I'm going to say 1 minus t times our infinite product. So product as n goes from 0 to infinity. 1 minus a t q to the n divided by 1 minus t q to the n. And what I'm going to do is I'm going to separate out the n equal to 0 term. I'm going to remove that from the product. So when I do that, I'm going to get 1 minus t. So this is our 1 minus t that we have outside. And when n is equal to 0, the numerator is 1 minus at times q to the 0, and the denominator is 1 minus t. So I can pull this out, and I'll write the remainder of the product. So as n goes from 1 to infinity, of 1 minus at q to the n divided by 1 minus t q to the n. The other thing that I notice right away is that the 1 minus t's will cancel out. Right? So once I've canceled the 1 minus t's, I get this rather nice expression of 1 minus at times the product, n going from 1 to infinity, of 1 minus at q to the n over 1 minus t q to the n. What I do next is I reindex. So I'm going to replace all my n's with n plus 1. So when I reindex this series, I'm going to end up with 1 minus at, so that stays the same. But now I want to start my product at n equal to 0. So this is going to be 1 minus at q to the n plus 1. Right? I have to still make sure that the first power of q is q to the 1. So n becomes n plus 1 when n is equal to 0. And 1 minus t q to the n plus 1. And what do I notice from this? Well, what I can do is I could pull 1 power of t off, or rather 1 power of q off and include it with the t. So I'm going to do that. I'm going to write this as 1 minus at, product as n goes from 0 to infinity of, let's write the numerator this way, 1 minus a tq q to the n. And let's write the denominator this way, 1 minus tq q to the n. Right? And then I notice that this product that I have here, this product is nothing more than f of t, but t has been replaced by tq. Right? So the thing that I might notice here is that this is just 1 minus at times f of tq. So we have this nice recursion that our function satisfies, right? We have this very elegant recursion that our function satisfies. Namely, we've shown that 1 minus t times f of t is equal to 1 minus at times f of tq. Right, so we'll use this. And we also know that a sub 0 is equal to 1. Right, so these are the two pieces of information I'm going to want to use when I try to find a sum side expression for f of t. Right, when I try to find the sum side expression. Okay, so let's try to find the sum side expression for f of t. All right, so right now we're starting with f of t as this product side, and what I'd like to do is compute these a sub n's. Right, so we're going to use this recursion to do that. Okay, so let's begin. So first thing to recall from just a second ago is that we're writing f of t is the sum of an t to the n as n goes from 0 up to infinity. So what I'm going to do is I'm going to substitute this into my recursion. Right? When I substitute this into my recursion, I'm going to get 1 minus t times the sum of a sub n t to the n goes from 0 to infinity. That's the left-hand side. And this is going to equal 1 minus at times the sum a sub n tq to the n as n goes from 0 to infinity. All right, so I've substituted this into my recursion. And what I'm going to do is I'm going to take this right-hand side and rewrite it a little bit more nicely. So I'll write this as 1 minus at times the sum of a sub n q to the n t to the n as n goes from 0 to infinity. Right, so we have this expression. Our goal again is to find what the a sub n's are. Can I solve for the a sub n's? Right, so let's expand this out. So I'm going to expand out the left-hand side and the right-hand side. So left-hand side is going to become, well, it's the sum of an t to the n times 1. And I'm going to multiply by t now. So I'm going to get the sum of an t to the n plus 1 as n goes from 0 to infinity. So this is what our left-hand side becomes. What does our right-hand side become? Well, when I expand this out, our right-hand side becomes the sum of a sub n, q to the n, t to the n. n goes from 0 to infinity. So this is when I take 1 times that sum, and then I have to take minus at times that sum. So what I'm going to get is minus the sum n goes from 0 to infinity of a sub n, a q to the n, t to the n plus 1, right? So I'm left with an expression of this form. Once I have this expression, what I'm going to do is I'm going to rearrange the sum a little bit. So I'm going to rewrite this. Namely, what I'm going to do is I'm going to swap two terms. I'm going to take this term right here and bring it over to the right-hand side. And I'm going to take this term right here and bring it over to the left-hand side. So we'll make that substitution, or rather that change to our equation. So I'm going to write this equation as the sum n goes from 0 to infinity of an t to the n minus the sum of an q to the n t to the n goes from 0 to infinity. And this is now going to equal the sum of an t to the n plus 1 n goes from 0 to infinity minus the sum an times a q to the n t to the n plus 1 as n goes from 0 to infinity. Okay, so what I'm going to do is I'm going to combine these into single sums. So the left-hand side, I can rewrite this as the sum n goes from 0 to infinity of an times 1 minus q to the n times t to the n. And the right-hand side, I can write this as an times 1 minus a q to the n times t to the n plus 1 as n goes from 0 to infinity. So now I've combined both of these sums into single sums, right? So I combine the left-hand side into a single sum, the right-hand side into a single sum. The one thing I might notice is if I look at this left-hand side, when I substitute n is equal to 0, I'll notice that the product in the middle becomes 1 minus q to the 0. So that term in the middle just becomes 0, right? It becomes 1 minus 1, which is 0. So this left-hand side, I can just write this as the sum n goes from 1 to infinity of an 1 minus q to the n t to the n, right? Because when n is equal to 0, that 1 minus q to the 0 term, that's just 1 minus 1, that becomes 0. And on the right-hand side, I can reindex this a little bit, right? So I could write this as the sum. I'm going to replace all my n's by n minus 1s. So this becomes a sub n minus 1, 1 minus a q to the n minus 1, t to the n. And now n has to go from 1 to infinity, right? So I have a sum that looks something like this. And what I'm going to do is I'm going to compare coefficients, right? Because now if I look at my equation, I have a t to the n on both sides. I have a sum that goes from 1 to infinity on both sides. So I'm going to compare coefficients. So I'll say comparing coefficients. I have the following very nice expression. I have that an times 1 minus q to the n is equal to a sub n minus 1 times 1 minus a q to the n minus 1. And this holds for n greater than or equal to 1. Right, so I have this nice recursion now satisfied by my coefficients. And the nice thing is I can solve this recursion. So I can rewrite this as an is really just an minus 1 times 1 minus a q to the n minus 1 divided by 1 minus q to the n for n greater than or equal to 1. And I already know that a0 is equal to 1 from earlier. Right, so I already know that this a0 term is equal to 1. So what does this give me? Well, let's try to solve for these an's, right? So hence, well, let's think about this. An is, again, it's 1 minus a q to the n minus 1 over 1 minus q to the n times a sub n minus 1. Now I apply the same recursion to a sub n minus 1 and rewrite it in terms of a sub n minus 2. So I'm going to get 1 minus a q to the n minus 1, 1 minus a q to the n minus 2 divided by 1 minus q to the n, 1 minus q to the n minus 1, a sub n minus 2. And we continue this way, right? We now apply the recursion to a sub n minus 2, so on and so forth. And continuing this way, we end up with, well, eventually we have to stop at a0. So we'll end up with 1 minus a q to the n minus 1. Eventually, we're going to hit 1 minus a. in the denominator, we're going to have 1 minus q to the n. Eventually, we'll hit 1 minus q. And this will be times a0, so times 1. And what have we ended up with? We've ended up with this very nice expression. This numerator is just a sub n. This denominator is q sub n. All right, so hence, we can conclude that f of t is really just the sum of a sub n over q sub n, t to the n, as n goes from 0 to infinity. And this proves this theorem by Cauchy. This proves our result by Cauchy. Okay, so our very first corollary of this theorem is going to be a result due to Euler originally, but it's actually a quick just corollary of this theorem. So we'll call this corollary 1a. And the result is basically, well, we just say 1 plus the sum of t to the n divided by 1 minus q squared, all the way up to 1 minus q to the n, as n goes from 1 to infinity. This is simply equal to the product of 1 minus t q to the n inverse. N goes from 0 to infinity. And another way of writing this is to, well, if we use our Q-Pockhammer notation, is to just say the sum of t to the n over q sub n goes from 0 to infinity, is equal to 1 over t sub infinity. So it's a rather elegant result if we use our Q-Pockhammer notation. So the proof is really straightforward. The proof is basically just plug a equal to 1, or sorry, rather a equal to 0 into the theorem above. Right, so if we plug a equal to 0 in the theorem above, let's take a look. We see that this term up here just becomes 1, right? Because we'll have 1 minus 0 times 1 minus 0 times 1 minus 0, so on and so forth. The denominator remains unchanged. If I plug a equal to 0 into this term, this becomes, again, a product of 1 times 1 times 1 n times, and this denominator remains unchanged. So just simply plugging in a equal to 0 gives us our theorem. Okay, so this corollary is, I mean, it's there, it's just not that terribly interesting. There is a more interesting corollary that follows from this. And again, we'll need that more interesting corollary. So let me put a little box here to indicate that we're done with this proof. And let me maybe, let's maybe write down the next corollary. So this will be corollary 1b. So it will be corollary 1b. Okay, corollary 1b says the following. It says 1 plus the sum of t to the n, q to the n times n minus 1 over 2, divided by 1 minus q squared, all the way up to 1 minus q to the n, as n goes from 1 to infinity, is actually just equal to the product of 1 plus t q to the n, as n goes from 0 to infinity. And if we want to write this again using our Q-Pockhammer notation, this is quite elegant. Using our Q-Pockhammer notation, this is really just saying t to the n, q to the n times n minus 1 over 2, divided by q sub n, and goes from 0 to infinity. This is just equal to negative t sub infinity. So it's really, really elegant when we use our Q-Pockhammer notation. Okay, so how do we prove this? How do we prove this theorem? Or rather, how do we prove this corollary? Well, the first thing we're going to do is we're going to look at our theorem, and we're going to replace a by a over b and t by bt. So we're going to replace a with a over b and t with bt in the theorem. Okay, so when we do that in our theorem, what does our theorem become? Well, this becomes 1 plus the sum, n goes from 1 to infinity. Our numerator, we're replacing the a with a over b. So this is going to become 1 minus a over b. 1 minus a over b times q. So on and so forth, 1 minus a over b times q to the n minus 1. Divided by, well, the denominator stays the same. So this will be 1 minus q squared, up to 1 minus q to the n. And we're replacing t by bt. So our t to the n is just going to become b to the n times t to the n. What happens on our product side? Well, on our product side, we're going to have the product as n goes from 0 to infinity of 1 minus, so a gets replaced by a over b, so we have an a over b. T gets replaced by bt, so we're going to have a bt here, and q to the n stays unchanged. And then in my denominator, I'm going to have a 1 minus bt q to the n, because t is getting replaced by bt. We might notice right away there's some interesting stuff that happens. Well, the first thing to notice is that, well, these b's cancel. Right, so first thing I'll notice is that the two b's on the right-hand side cancel. The other thing I might notice is that I have n b's that occur over here. So what I'm going to do is I'm going to take each one of these b's and distribute them into this expression here. So there's going to be one b that goes here, there's one b that goes here, and the nth b is going to go here. So I'm going to take these b's and kind of distribute them through. So I'm going to take each power of b and kind of distribute it in. What is that going to turn our expression into? Well, our expression turns into 1 plus the sum, n goes from 1 to infinity. Well, 1 minus a over b times b is just going to be b minus a. 1 minus a over b times q, all of that times b just becomes b minus aq. And we continue until we hit the very last term. We're going to get b minus a q to the n minus 1. And I'm going to divide by 1 minus q, 1 minus q squared, all the way up to 1 minus q to the n. The right-hand side, we've already basically simplified, right? The right-hand side is just the product n goes from 0 to infinity of 1 minus a t q to the n divided by 1 minus bt q to the n. All right, so the right-hand side's already in its simplified form. Okay, so we've taken our core, remember, we've taken our theorem, we replaced a by a over b, we replaced t by bt, and we've achieved this result so far. Okay, and I forgot to write a t to the n over here, so I'll put that t to the n in over here. Okay, so what are we going to do next? We're now going to we're going to set b equal to 0 and a equal to -1. So I'm going to set b equal to 0 and a equal to -1 in this expression. All right, so when I do this, what do I end up with? I end up with 1 plus the sum, n goes from 0 to infinity. Again, I'm setting b equal to 0, a equal to -1. So the first term becomes 1. The second term becomes 0 plus 1q, so this becomes q. The next term is going to be q squared, and we're going to continue until we hit q to the n minus 1, divided by 1 minus q, 1 minus q squared, all the way up to 1 minus q to the n. And of course, we have this t to the n on the outside. What happens to the right-hand side? Remember, I'm setting b equal to 0 and a equal to -1. Well, if I set b equal to 0, the denominator just becomes an infinite product of 1s, because it's 1 minus 0 infinitely many times. And the numerator becomes 1 plus t q to the n as n goes from 0 to infinity. So we now have an expression that looks something like this. And we can kind of simplify this just a little bit more. So this numerator right here becomes the sum is 1 plus the sum, n goes from 0 to infinity, of q to the 0 plus 1 plus 2 plus ... plus n minus 1 over 1 minus q, 1 minus q squared, up to 1 minus q to the n. So I'm just combining all the powers of q in my numerator. And the product side, again, I'm not touching. I'm going to leave this be, because it's already our desired product side. It's already our desired right-hand side, so we don't have to do anything here. And we're going to use one more fact, right? So the thing to recall is if I take 1 plus 2 plus 3 plus, if I take the sum of the first n minus 1 integers, this is nothing more than n times n minus 1 over 2, right? So what does our result become? This becomes 1 plus the sum, n goes from 0 to infinity, of q to the 1/2 times n minus 1, divided by 1 minus q up to 1 minus q to the n. T to the n is equal to the product of 1 plus tq to the n as n goes from 0 to infinity. And this finishes the proof of our corollary. Okay, so also just to note a quick typo correction that I made here, the sums should all start with n going from 1 to infinity. I made a typo there and I wrote n equals 0 to infinity. But the material in the proof is correct, just a small typo. Okay, so now we explore some important corollaries of corollary 1b and corollary 1a. So what I'd like to do is to make certain important substitutions, and these important substitutions will be relevant to when we prove the Jacobi triple product identity. So I'm going to start with corollary 1b. I've written in this form, and the substitution that I'm going to make, so I'll write some important substitutions. So important substitutions. The very first one I'm going to do is I'm going to do this a little bit carefully. So the first thing I'm going to do is I'm going to substitute I'm going to replace every instance of q with q squared. And after that, I'm going to replace every instance of t with z times q. Right? So these are the substitutions that I'm going to make inside of corollary 1b. So inside of corollary 1b. And what does our expression become? Let's be a little bit careful about this. So this becomes the product of 1 plus zq times q to the 2n. And goes from 0 to infinity. So I've replaced all my t's with zq, and I've replaced all my q's with q squared. So I've done it in the order that q gets replaced by q squared first, and then t gets replaced by zq. And what happens on the right-hand side? Well, I'm replacing t by zq and q by q squared. So the q power becomes q squared to the 1/2 m times n minus 1. So this becomes q to the m squared minus m. Right? The 1/2 disappears. It gets canceled by the q squared. And what happens with the t term? This becomes z to the m, q to the m. Right? And in the denominator, I'm going to have q squared sub m. M goes from 0 to infinity. Okay, so how does this simplify? Well, there's a little bit of cancellation that happens. So to write this a little bit more elegantly, this will be the sum n goes from 0 to infinity of 1 plus zq to the 2n plus 1 is equal to the sum m goes from 0 to infinity of z to the m, q to the m squared, divided by q squared sub m. And we'll write this equation down. We'll kind of keep it to the side. I will call this equation star. So this will be our very first equation that we want to save. This will occur in the proof of the Jacobi triple product identity. Okay. So this is our very first corollary of our corollary. All right, so it's the very first substitution that we make. Now what I'm going to do is I'm going to take equation 1b and make another substitution. Right, so let's kind of write down corollary 1b again for our purposes, and let's make another substitution. So what's the substitution I'm going to make? So now what I'm going to do is I'm going to substitute q is going to get replaced by q squared. And then after I do that, t is going to get replaced by negative q to the 2m plus 2. All right, so this is the substitution that I'm going to make. So let's write this out a little bit carefully. So this is going to become the product of 1 minus q to the 2m plus 2, q to the 2n, and goes from 0 to infinity. And since I'm using m over here, I'm going to use a different index of summation for the sum. I'll use r. So this will be the sum r goes from 0 to infinity. And what does this become? This becomes minus q to the 2m plus 2 to the r, q to the r times r minus 1, so r squared minus r. And then at the bottom, we get q squared sub r. And again, the sum I know is initially written in terms of m. So instead of using this m up here, we've used r as our index of summation. Okay, so let's clean this up just a little bit. What does this become? This becomes the product as n goes from 0 to infinity of 1 minus q to the 2n plus 2m plus 2. And on the right-hand side, we end up with the sum r goes from 0 to infinity of, well, we have a negative 1 to the r, a q to the r squared minus r, right? That's coming from the second term, and then a plus 2mr plus 2r. All right, so our expression looks something like that. In our denominator, we end up with q squared sub r. Okay, so let's clean this up just a little bit. The left-hand side, we actually notice one way to rewrite this is to use our q Pochhammer symbol. We can write this left-hand side as q to the 2m plus 2 q squared sub infinity. And on the right-hand side, I can just clean up the exponent a little bit. This is going to be the sum, r goes from 0 to infinity, of -1 to the r, and this is going to be q to the r squared plus 2rm plus r. All right, so I could just clean up that exponent a little bit, and at the bottom, I'll get q squared sub r. Okay, and this equation is an equation that I'll call equation star star. Right, so this is an equation star star. Right, so when I refer to equation star star, I'll be talking about this equation. The interesting thing about this equation is that if m is equal to 0, or rather, sorry, if m is less than 0, the left-hand side is equal to 0. So one thing that I'll note is that if m is less than 0, then there's a term that looks like 1 minus 1 that appears in the product. So this appears in the product side on the left. Right. So one thing that I noticed that's kind of remarkable about this is that q to the m plus 2 q squared sub infinity is equal to 0 if m is less than 0. Okay, so this is kind of a nice little remarkable fact about this expression here. Okay, and finally, we have one more substitution that'll lead us to equation star star star. Right, so what's our last substitution? Our last substitution, again, relies on corollary 1a. So I'll just remind us what corollary 1a is in this case. Corollary 1a, again, I'll reindex and write it in terms of r instead. This is t to the r divided by q semicolon q sub r. R goes from 0 to infinity. This is equal to 1 over t semicolon q sub infinity. Okay, so what I'm going to do is I'll make the following substitution. So I'm going to substitute, I'm going to replace q with q squared first. Then I'm going to substitute t and replace it with negative q z to the minus 1. All right, so I make this substitution. And what does my expression become? This becomes the sum, r goes from 0 to infinity, of minus q z to the minus 1 r divided by q squared sub infinity. And what does the right-hand side become? This becomes 1 over minus q z to the minus 1 q squared sub infinity. And so this expression we will call equation star star star. Right, so this will be equation star star star. Okay, and we'll use all three of these expressions in our proof of the Jacobi triple product identity in just a minute. Okay, so now we're finally ready to prove the Jacobi triple product identity. So we're going to use every piece we've established in this video and use it in our proof. Okay, so let's begin our proof. So this is the Jacobi triple product identity. At the top, our goal is to prove this equation. Okay, so the proof begins as follows. So I'm going to take this product. It's going to be 1 plus z q to the 2n plus 1 as n goes from 0 to infinity. And this might look familiar because this is the expression that appeared inside of equation star. Right, so this is our very first equation. So by equation star, I can write this as z to the m q to the m squared divided by q squared sub m. So q squared semicolon q squared sub m, and m goes from 0 to infinity. And this is by equation star. Right. The next thing I'm going to do is I'm going to take that denominator and rewrite it. All right, so using our fact from the beginning of this video, so one of our basic properties of q Pochhammer symbols, I'm going to take this denominator and rewrite the sum as the sum z goes from 0 to infinity of z to the m q to the m squared times q to the 2m plus 2 q squared sub infinity divided by q squared sub infinity. All right, so this is one of our basic properties of q Pochhammer symbols. I'm rewriting it in the following way. Right, essentially the substitution I'm doing is, the substitution I'm making is 1 over q squared q squared sub m is equal to q to the 2m plus 2 q squared sub infinity divided by q squared sub infinity. All right, so it's just a cancellation like in our earlier proof. Okay, the next thing I'm going to recall is that this numerator is equal to 0 whenever m was negative, right? So we established earlier that whenever m was less than 0, this numerator was 0. So rather, more specifically, I guess, is this term in the numerator becomes 0 when m is less than 0. So I'm going to write this in the following way. I'm going to pull the 1 over q squared sub infinity out of the sum, and I'll write this as the sum m goes from minus infinity to infinity of z to the m, q to the m squared times q to the 2m plus 2 semicolon q squared sub infinity, right? And this is since q to the 2m plus 2 semicolon q squared sub infinity is equal to 0 if m is less than 0. All right, so I can rewrite this expression this way. Basically, I've just introduced infinitely many zeros into my expression. Okay, now what am I going to do next? The next thing I'm going to do is I'm going to look at this expression right here and use equation star star to rewrite it. All right, so if I use equation star star, what ends up happening? Well, this becomes 1 over q squared semicolon q squared sub infinity. That stays the same. This becomes the sum, m goes from minus infinity to infinity, of z to the m, q to the m squared. And now when I use equation star star to rewrite this q Pockhammer symbol, I'm going to get the sum of negative 1 to the r, q to the r squared plus 2mr plus r divided by q squared semicolon q squared sub r, and r is going to go from 0 to infinity. So this is now I'm using equation star star to do this. All right, this is equation star star that's getting me here. And what I'm going to do is I'm going to rewrite this. All right, I'm just going to do some algebra here and rewrite this. So this is going to be 1 over q squared sub infinity. And I'm going to write this as the sum. M goes from minus infinity to infinity. The sum, r goes from 0 to infinity. And I'm going to rewrite this in the following clever way. I'm going to move the negative 1 to the r to the front. I'm going to write this as q to the r squared plus 2mr plus m squared, z to the m plus r, q to the r, and z to the minus r, divided by q squared sub r. And I'll let you check that these terms actually work out. The thing to notice is that z to the m plus r times z to the minus r give us our z to the m, right? So that's kind of what's going on here. I'm just doing this kind of like a clever substitution. And what I'm going to do is do a little bit more algebra and kind of separate some of these terms out, right? So let's do a little bit more algebra. I'll write this as 1 over q squared sub infinity. And now I'll write this as the sum, r goes from 0 to infinity, negative 1 to the r, z to the minus r, q to the r, divided by q squared sub r. And then I'll write the sum, m goes from minus infinity to infinity, of q to the m plus r squared, z to the m plus r. All right, so I get this nice expression once I rearrange my terms appropriately. Notice that this exponent, this q to the r squared plus mr plus m squared, and there's a typo up there, this should be plus 2mr, so let's correct that. Good thing we caught that, plus 2mr. This expression right here becomes q to the m plus r squared, right? And our z to the m plus r becomes the z to the m plus r here. The rest of the stuff I'm gonna rearrange and pull out of the sum. Okay, so I get an expression that looks like this. The other thing I'll notice is that I'm summing, when I look at this right-hand sum, I'm summing over all the integers, right? So for every fixed value of r, I'm summing over all possible values of m. So now I'm going to reindex this. I'm going to replace all my m's by m minus r's. All right, so I'm going to reindex this, and I'll still be summing over all the integers. So this is 1 over q squared sub infinity, sum, r goes from 0 to infinity, of -1 to the r, z to the minus r, q to the r, divided by q squared semicolon q squared r. And now I'm going to write this sum as m goes from -infinity to infinity of q to the m squared z to the m. All right, and so what I've done is I've reindexed I've replaced m by m minus r. Right, but I'm summing over all the integers, so it's kind of inconsequential. It doesn't change the limits of the summation. Okay, so we have something elegant that looks like this. And the one thing you might notice right away is this can be written as a product, right? So namely, I can write this as 1 over q squared sub infinity times this term, right? And the thing in the middle, the term in the middle might look familiar, right? This is the expression that appeared inside of equation star, 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 right? So this is our equation star, star, star. So let's maybe rewrite this in a more elegant way. This is q squared semicolon q squared sub infinity times the sum. Let's write it this way, -1 to the r, q z inverse to the r, divided by q squared sub r. R goes from 0 to infinity. And then times the sum of q to the m squared, z to the m. M goes from -infinity to infinity. And again, now I have something that I can use equation star, star, star to substitute for, right? So if I take that middle term and substitute it, right, I have this beautiful equation star, star, star that I can use. This becomes 1 over minus q z to the minus 1 semicolon q squared sub infinity times the sum of q to the m squared z to the m as m goes from -infinity to infinity. So this is by equation star, star, star. Right? And essentially we're done, right? So what we've done is we started with this infinite product, and we've shown that it's equal to rather this product times the sum. And so what I can now do is I can rewrite my expression, right? So I could take this expression and rewrite it. So let's do that. So rewriting, what is this really saying? This is really saying that the sum of q to the m squared, z to the m goes from -infinity to infinity, is equal to the product that we started with, this 1 plus z q to the 2n plus 1, and goes from 0 to infinity, times these q Pockhammers that we've just written down. So q squared sub infinity, and minus q z to the minus 1, q squared sub infinity. And if we think about what these are, well, this term right here is 1 plus z q to the 2n plus 1. This one stays the same and goes from 0 to infinity. This term right here is going to be 1 minus q to the 2n, as n goes from 0 to infinity, rather, or I guess I'll write 2n plus 2 because n goes from 0 to infinity. We don't want to include 1 minus 1. And then this last term right here is just 1 plus q, rather, 1 plus z inverse q to the 2n plus 1. And we've proved our Jacobi triple product identity. Okay, and the last thing I want to discuss now is just some clever rewritings of the Jacobi triple product identity, because ideally, when we look at the sum on the left-hand side, summing over all possible integers is not so great, right? The left-hand side is a power series in Q, but summing over all possible integers is not ideal. So let's talk about some ways of rewriting this. So the first thing we can do when we look at the Jacobi triple product identity is replace z with negative z. Right. So when I do this, the triple product identity, it's still the sum on the left-hand side is still the sum from -infinity to infinity. But now we have a -1 to the m, q to the m squared, z to the m. Right. The idea is that z becomes negative z, so negative z to the m is just -1 to the m times z to the m. And the right-hand side is a little bit nicer looking as well. So this becomes the product n goes from 0 to infinity of 1 minus q to the 2n plus 2. 1 minus z q to the 2n plus 1, and 1 minus z inverse q to the 2n plus 1. And the reason we do this is, well, we're going to want to rewrite the Jacobi triple product identity in a nicer form, and the nicer form is going to be what's useful for our proof later on of the Rogers-Ramanujan identities, right? So the substitution of z to minus z is just because it'll be useful later on for us. Okay, so again, summing over z is quite inconvenient. right? So what I'm going to do is I'm going to break this left-hand side up into three pieces. I'm going to break it up into the sum m goes from negative infinity to -1. I'm going to look at the m equals 0 term, and I'm going to look at the sum as m goes from 1 to infinity. So first, let's look at this right-hand side. So I'm going to take this right-hand side, this -1 to the m, q to the m squared, z to the m, as m goes from -infinity to infinity, and I'll rewrite it in the following way. I'll say this is the sum, m goes from -infinity to -1, -1 to the m, q to the m squared, z to the m, plus 1, that's our m equal to 0 term, plus our sum, m goes from 1 to infinity, of -1 to the m, q to the m squared, z to the m. Okay, and what I'm going to do is in this left-hand sum, or rather, yeah, in the sum on the left, I'm going to replace m by -m. So I'm going to reindex this sum. I'm going to reindex this sum. So what does this sum look like if I replace m with -m? Well, this becomes the sum m goes from 1 to infinity. -1 to the m and -1 to the minus m, those are the same. So this becomes -1 to the m. Q to the -m squared is the same as q to the m squared. The only thing that's going to change is this becomes z to the minus m. The middle term is 1, and the latter sum is still the same. So I haven't changed this. So this is the sum -1 to the m, q to the m squared, z to the m. So now I have an expression that looks something like this. Finally, what am I going to do? I'm going to combine the sum on the left and the sum on the right-hand side. So let's combine those two. So I could write this now as 1 plus the sum. If I take this expression here and this expression here, I look at the terms they have in common. They both have a -1 to the m in common. They both have a q to the m squared in common. And what I can do is I can pull a z to the m out from both of them, right? And I can now rewrite this as, well, what's left over? I'm going to have a 1 plus z to the minus 2m. And I can check that this expression that I've gotten here equals this expression up here by just distributing, right? So z to the m times 1 gives us the z to the m, and z to the m times z to the minus 2m gives us the z to the minus m, right? So I can just check this by redistributing. And so I've rewritten, I guess I should write m goes from 1 to infinity here also, keep my summation straight. But I've now written my Jacobi triple product identity sum side in a slightly easier to handle way, right? So I've written this equation as 1 plus the sum, m goes from 1 to infinity, of -1 to the m, q to the m squared, z to the minus m, 1 plus z to the 2m, rather minus 2m. Yeah, minus 2m, and z to the m over here. And this product side is going to be the product 1 minus q to the 2n plus 2, 1 minus z q to the 2n plus 1, 1 minus z inverse q to the 2n plus 1, as n goes from 0 to infinity. So this is another formulation of the Jacobi triple product identity, right? This is just another formulation of the Jacobi triple product identity. I will leave you with an exercise. So try the following exercise. Good practice with this type of stuff. Try to rewrite the Jacobi triple product identity sum side as the following. The sum m goes from 0 to infinity of -1 to the m, q to the m squared, z to the m, times 1 minus q to the 2m plus 1, z to the minus 2m minus 1. And of course, this is just going to equal our normal product side. So 1 minus q to the 2n plus 2, 1 minus z q to the 2n plus 1, and 1 minus z inverse q to the 2n plus 1. All right, so this is just our normal product side. So I'll leave this as an exercise. It uses a similar trick. It's a little bit more complicated than the rewriting that we had above, but we will also use this later on when we study the proof of the Rogers-Ramanujan identities. Okay, so I'll stop here.